Problem number 5 is going to ask you to write your own recursive definition for each sequence. So before we do that, let's just make sure that we have a good solid sense of what a good recursive definition means. An excellent place to look for examples is the true answers in question number 4. So for example, number 4, letter A, which we sort of talked about together in the previous video, could be an excellent example or template to follow for what a good recursive definition looks like. A good recursive definition definitely needs to have 2 things. A starting term, so some specific term that you want to call out. And usually it's the first term, but it can be any term. It can be the 0 term, it could be a random term in the sequence. Any starting term is completely fine. And then you'll need the actual equation itself, the part that tells you in terms of t of n what exactly is going on. So the equation is always going to have the same structure, the t of n plus 1 equals t of n, and then the operation. So if it's a sequence that's adding 11 like this one, t of n plus 11. If your sequence is subtracting 10, t of n minus 10. If your sequence pattern is multiply 4, t of n times 4. So whatever operation needs to happen in order to make the sequence keep going, that's what you specify in the equation spot. So, knowing that you have that bit of a template, go down to question number 5, letter A, and let's try to write a recursive definition for 3, 9, 27, 81, and so on. Generally speaking, you can choose which term you want to define as your starting term, but to keep it simple, I would recommend that you use the first term just because that is the first thing you're given. They started you with the 3 and gave you the subsequent terms. So you might as well kind of repeat what you started and just stick with defining the first term. Remember, to define the first term, we call it t of 1 equals. That means the first term is 3. So that's how we define the first part of our recursive definition. T of 1, first term is, and then we write the value of the first term. First term is 3. Now we write the recursive equation. T of n plus 1, which translates into saying the next term can be found by equals taking whatever you have for the current term, t of n, and then looking at this pattern, I can see, oh, well, the pattern is multiplying 3, because 3 times 3 is 9, times 3 is 27, times 3 is 81, so t of n times 3. Now, you'll definitely see this answer represented in different ways depending on if you look at answer keys or not. So another way you might see this answer represented is to have the same starting term, but a slightly different cosmetic version of the recursive equation itself. And that could happen. Sometimes we put times 3 as a constant in the front instead of afterwards. It doesn't matter. Both of these answers are exactly the same. It would also be fine if you wanted to give yourself another option to actually define a different term. You could say that the second term is 9, which is factually true, and use the exact same equation. That would also be mathematically correct. So it's totally up to you to decide how you want to define your first term. I usually keep it simple and just use the first one they give me, but that's fine. And it is a little bit your discretion as to whether you format your equation in a traditional way or if you rearrange some things. Those are just small cosmetic differences that don't matter. It's just up to you to decide if you want to make those tweaks for yourself or if you're fine with writing it as just what it is. Like to get the next one, take the current one, times by 3. That might translate very literally for some people in a natural way, so they prefer to write it like that. In any case, we can try one more just to kind of make sure that you've got the idea. I'll look at letter B, and then I'll have you try some on your own. In letter B, again, keep it simple and try to define yourself a starting term. Again, they gave me that the first term is 17, so I'm just going to use the path of least resistance, so to speak. I'm just going to use what they gave me. First term, 17. Done. I can tell that the pattern after 17 is to subtract 2 each time, so that subtracting 2 is going to be the main part of my recursive equation itself, the t of n plus 1 equation. So t of n plus 1 equals, the next term is the current term, t of n, minus 2. So notice again, 2 parts of the answer, And that's why the answer space, you'll notice, is a bit more generous than usual. That's because these answers do require 2 parts to them. But hopefully now that you've seen the structure or the format, you can take some time to try letters C and D. After you take some time to try letters C and D, question number 6 is going to essentially have you do kind of the opposite. Number 6 is giving you a recursive definition and asking you to write at least 4 terms of the sequence. Basically the exact opposite of what they did in 5, where they gave you 4 terms of the sequence and wanted you to write the definition. So in number 6, and I'll again just do one problem as an example, I'll do letter A. Think about the fact that they're going to give you one specific term. It doesn't matter which term they give you. They just want any 4 terms in the sequence, so it doesn't matter if it's the first one, the 5th one, anything. It's just a random starting spot. So this one tells us that T of 1, so the first term, is 6. So I'm going to kickstart my list of terms with a 6 because I know for sure that's happening. The n+1 equation, the recursive equation, tells me what to do afterwards. So if I translate this thing, it looks like this is taking the T of n and multiplying by 3. I probably would have written it as T of n times 3 if I was writing my own equation, but it's okay, because again, cosmetic differences don't change the nature of the math. 3 times T of n is the same as T of n times 3. But times 3 is the most important part there. Times 3 is the part that tells me, oh, that's the pattern. That's what's happening to the sequence. The sequence numbers are each going to be multiplying by 3. So 6 times 3 would give me 18. Now I know the next term. 18 times 3 would give me 54. That would give me the next term. And 54 times 3 is 162. So that would give me a 4th term. Now it happens to be that I have the 1st, 2nd, 3rd, and 4th terms, but it doesn't matter which terms in the sequence you have. If you want to make a little table of values, you certainly can, and you can label which terms in the sequence you have. So for example, if I wanted to kind of make my answer space a little bit more detailed, I could say that 6 is the first, 18 is the second, and so on and so forth. Or you can just write the list of numbers. When you check the answer key, you'll just see a list of numbers. But in any case, that hopefully will give you an idea of how to start getting familiar with the format of a recursive equation and how to make sure that it helps kind of communicate to your brain the crucial parts of the list of numbers itself. Where to start the list or where to start the sequence, and then how to generate the next numbers in the list as you go forward. The last question that you're going to try today is question number 7, which is about the Fibonacci sequence. If you did the previous lesson that involves sorting all the different cards on Desmos, you may remember seeing the Fibonacci sequence, and it was the weirdest sequence because it didn't have any explicit pattern. It wasn't arithmetic, it wasn't geometric, and it wasn't quadratic. It was kind of like the one that stood out on its own. And its equation is actually only possible to define recursively. It's not actually an explicit pattern because you're not adding something consistently each time, because if you notice, the gap between 1 and 1 is 0, the gap between 1 and 2 is 1, the gap between 2 and 3 is 1, the gap between 3 and 5 is 2, the gap between 5 and 8 is 3. That's not truly arithmetic because you're not adding the same number every time. It's also not geometric because you're not multiplying by the same number every time. If your adder or your multiplier keeps fluctuating, then it's not a true arithmetic or geometric sequence. So the Fibonacci sequence is kind of a curious little sequence because of that weird loophole, but it can be recursively defined. In other words, you can actually write a recursive equation that works. So if you want to explore that a little bit, you can. If you want to use the answer key as kind of a jumping off point, you can do that too. And if you simply Google the phrase Fibonacci sequence, you'll actually find a fascinating series of videos and websites that kind of walk you through not only where the sequence came from, like who Fibonacci was and why it was so important to him, but also all of the different interesting applications of the Fibonacci sequence in the real world. Because weirdly enough, there are all sorts of connections to different phenomena that seem completely unrelated and yet have a Fibonacci pattern at their core. The spiral of seeds in the center of a sunflower, conical type shapes that appear in nature with like weird types of cauliflower. There are all of these natural organic things that actually have a Fibonacci pattern to them. which is kind of eerie to think that nature somehow has this super predictable numerical pattern built in, and yet it does. So it's actually a really fascinating little rabbit hole to go down, and I would totally recommend that if you have the time, that you kind of give yourself the opportunity to click around a little bit and look at all the different far-reaching implications that the Fibonacci sequence connects you to. Because there are implications in the worlds of art and architecture and all sorts of other stuff that might not even seem like it should be related, and yet all kind of fits together under this fascinating little umbrella. In any case, your last goal today is to finish numbers 5 and 6 for sure. And if you have time to explore 7, then great. But if you don't, I wouldn't worry about it too much. I would definitely focus on 5 and 6, check your answers on the answer key, and take some time to either take some notes or let the information kind of marinate so that you can really think on it before resuming before the next lesson, where we're going to take our understanding of recursive stuff and pump it up a little bit more. So that's why today's assignment is really just the basics. And then as a separate assignment, you'll do the subsequent pages where we start to put it all together.